So whoever is there will be able to see it. Whoever is there will be able to see it. Okay, so we're live on YouTube. So let's see now. So we're saying now, last time we did rates of reaction, collision theory, the Boltzmann distribution curve, we did all that stuff. And the students requested specifically that they wanted to do Hess's law for this week. We're waiting on those students, haven't seen those students join us as yet. So what I'm getting is from the students who are currently here, what's this that they want to delve a little bit more deeply in. And so people, Karina and Kimberly say chemical equilibrium. Karina says chemical equilibrium. Okay, so Frank, so that's three people who say chemical equilibrium. Devon said transition metals, and then Fran had said acid-base equilibrium. So like this whole equilibrium stuff, right? Chemical equilibrium is like a whole thing unto itself, right? And underneath that comes all these other ones. So like the acid-base equilibrium and all this stuff. Right, so let's see, chemical equilibrium is where it starts off. Then you have acid-base equilibrium. And then let's see what comes after acid-base. I think redox equilibrium, yeah, redox potentials and so on is under that as well. It's a whole lot, you know, that whole thing. So I can see why, you know, it would be beneficial to have a good grasp of this stuff. So let's see where we are now. Redox equilibrium is a bit confusing. Okay, let's see. Okay, let's see how I can best start this off and kind of do a little bit on equilibrium with you guys today. So I think that's a common thing that I'm getting from you guys here. So in the interest of time, we don't have the other students here. So let's get started with this. So chemical equilibrium, right? So I think that really, at a fundamental level, I'm kind of like just gonna go and talk with you guys, talk through this, right? And then wherever necessary, I will put up a whiteboard and write some stuff down. And well, let me see. In the meantime, just give me a minute, let me see. What? Can't miss this chemical equilibrium. Pull up any notes I have on chemical equilibrium on my end. This in. Let me see. I'm just gonna like talk it through to you guys, like have a conversation about it, like just like the basics, so that we have the fundamentals of it. Like I'm very big on fundamentals, right? Like if this is your first time here, you will see that I'm very big on fundamental stuff. So like I like to like lay the groundwork for stuff that I'm doing before building on or adding on. So like doing any kind of problems or anything like that. I like to like do fundamentals, right? So I'm just gonna like talk you guys through this stuff if that's okay with you. Let me know, thumbs up, thumbs down, let me know. Because I think that once you have a solid framework, a solid background, I think that you can then build on that and build forward and be very confident, right? In explaining stuff and knowing what comes next and what to do next, right? So I have something up on the screen about the chemical characteristics of the equilibrium state, right? But before we even go to talking about equilibrium state, you know, it's important to know that when we think about chemical reactions and reactions in general, we often, the way that we write equations, sometimes you'll see that we write them with, so I'm coming out of that box. So we have like this arrow. Sometimes when we write an equation, so we'd say A plus B, say it would go to C plus B, right? So we can write it like that. And we can also write it like this, where we have, say, A plus B, and we go like this. So when you look at those two things, can you tell me what the distinction is in the way that we've written that? Like what immediately jumps out at you in those, between those two equations? Like yeah, Devant, I see your hand is raised, go ahead.
This one is reversible, while one is not.
Exactly. So that's kind of this what this whole idea of an equilibrium state hinges on, right? It's like I mean, in top equation, we're showing you that you have that we would say, what would we say about that top equation? You said one is reversible and one is irreversible. So in essence, then what we say is that the top one kind of then goes to completion, right? It's completed, one of the reactants run out. And so it's irreversible, right? That's the top one. Okay, go ahead, Devant. I see your hand is raised.
Sorry about that, miss.
Yeah, go. Wait, did you have something to say? Or was it accidentally raised? Oh, okay, I guess it was an accident then. Okay, so I see that Beyonce and Anish just joined in. Welcome, Beyonce and Anish. So we have some new students this week, and they had mentioned that they wanted to just talk a little bit about chemical equilibrium. So that's kind of where I'm starting today, and then we can flip back, we can switch back over to Hess's law, because I know that last week you guys had mentioned that that's what you wanted to cover. So we're just going to do a little bit on chemical equilibria and then just hop back over to Hess's law if you're still interested in seeing that. So just write in the chat and let me know if you still want to see that stuff that you had mentioned last time. Okay, cool. All right, so we're talking about this whole principle or this whole idea of chemical equilibria hinges on, right? And we're saying in the first case here, I've written an irreversible, right, reaction goes to completion. In the second case, we draw, I just wrote like one that's that's reversible, right? And so reversible reactions, right? The forward and backward reactions take place at the same time. If it takes place at the same time, right, the rate at which the front one, the forward reaction takes place is the same as the rate of the backward one. We say that they have been entered into an equilibrium state, right? Whereas in the top one, it goes forward and it finishes forward and that's it. But for reversible, right, reactions, where the rate, so make sure you listen to what we're saying now, the rate of the forward reaction is equal to the rate of the backward reaction, we say that is in an equilibrium state, right? Are we good so far on that? With what an equilibrium state is? So equilibrium state, it's an equilibrium, or it's an equilibrium reaction, right? So that's what this whole equilibrium state, equilibrium principle hinges on. And so some several characteristics of it, then I have that written there in the box. So we're saying the characteristic of an equilibrium state is that it's dynamic, right? It's not static, it's dynamic. And by that, we mean it's constantly changing, right? So the molecules of the reactant, so that's A and B, are constantly being converted to products. And by that same token, the products, which are C and D, are constantly being then converted back to reactants. It's like a back and forth, it's a back and forth, it's a back and forth. And these things are happening at the same rate, at equilibrium. So at equilibrium, if it's in that equilibrium state, the rate of the forward reaction is equal to the rate of the backward reaction. So are we clear on these first two characteristics so far? Is that it's dynamic, it's not static. The opposite of dynamic is static. It's never like stopped. If it's stopped, it's like a completion. It's a complete reaction, that would be an irreversible reaction. But for the equilibrium state, it's dynamic. It's always happening. It's always changing, right? And then if they're in equilibrium, the rate of the forward conversion is the same as the rate of the backward conversion. So let me know if that's clear so far. So Levanta says yes, Fran says yes. All right. So let's go through the other two now. So the concentration, and we typically depict that like this. So we typically write concentration as, let me write that for you. We typically say, we would say concentration of A, right? You know, those square brackets. That's typically how we depict concentration, right? Concentration of A, we have a concentration of B, we have concentration of C, and we have concentration of D. That's how we typically write these in square brackets, right? Give me a thumbs up if you've seen that denotation before. Like that's how you write it, that notation before. So the concentration of reactants and products at equilibrium do not change, right? So the concentration does not change. If they're equilibrium, the concentration of the products and reactants isn't changing. They are constant. They are constant. That's a concentration now, you know, guys. So make sure you see what we're talking about here. We're saying that the concentration, which is this, right? It does not change. They are constant, and it's because the rate of the forward is equal to the rate of the backwards. They're the same rate. It's flipping this way, it's flipping this way at the same rate. So nothing is changing. They're in equilibrium, right? So those are we're on that same page. It's constant. The concentration is not changing, right? So then finally, equilibrium only occurs in a closed system. What do you mean by a closed system? In your own words, when we say a system is closed, what do we mean by that? What do we mean by that? Does anyone know? Does anyone know? Can anybody tell me what we mean when we say a system is closed and the opposite would be open? You have a closed system and you have an open system. Equilibrium can only occur in a closed system. What's a closed system? Exactly. Okay, so Kimberly said it remains the same. That is true. But I think Fran captured it more spot on, more accurately, is in saying that nothing is allowed in or out. It's closed, right? It's like it's sealed, right? Once it's sealed, nothing can come in and nothing can come out. So that's a closed system, and equilibrium can only occur in a closed system, because think of it this way, guys. Like if it wasn't a closed system and it was open and you could keep on adding things in like this. So like I don't know if you can see. Let me put this up here so I can see what you're seeing. Like I have this teacup. I always have a teacup because I love drinking tea. But like I have a teacup here, right? There's some tea in it. And yes, it's not closed from the standpoint of it's not covered. Right? So it's not covered, but if it were covered, just imagine my hand was a cover and it was covered, it would be a closed system, and I am not putting anything else in it other than what's already in it, right? So if it weren't closed, though, if it's not closed, I can keep on adding stuff in and increasing concentration of stuff. So say I have sugar in it, I don't, but if I had sugar in my tea, and it was an open system, I could continue adding in sugar, and that would continue to shift the concentration or the amount of sugar that I have in it. So how would that reach equilibrium if I'm constantly changing the variables myself, right? It would kind of be a weird scenario. So for equilibrium, it needs to be closed off. So you have a set amount of both things in there. And so, yeah, and so generally then that's what we mean by a closed system. A closed system is one where none of the product or reactant escape from the reactant mixture. It has many reactions, however, can take place in open beakers if the reaction takes place in solution and no gases are involved. And by that, it means that if it's a solution and the beaker is open, right? If it's a solution and the beaker is open and there are no gases involved, then you're still kind of, it essentially still functions as a closed system because no gas is leaving and no gas is going in per se. It's just a solution, whatever is in that solution, that's gonna be constantly in that dynamic state, right? So it functions as a closed system, but you need a closed system for equilibrium. You can't be changing the dynamics yourself, if that makes sense. For equilibrium, it's a closed system, and what's in it is going to eventually, that's what's finding that medium and that balance of the rate of fall being the rate of backward. You're not putting in anything to make it go one way or another. So when we say a closed system, that's what we mean. It's closed off from anything coming out or anything coming in, right? So is that clear? Is that clear to you? All right, so that's good. So that's our first, fundamental stuff. Characteristics of the equilibrium state. You have to be able to be comfortable with that, right? So we spoke about reversible reactions and equilibrium reaction, the same as equilibrium reactions, because the backward motion, the forward motion from a rate constant standpoint, they're equal, they're equivalent. And so it's important to note then that the first equation that I wrote when I had that irreversible arrow, when we contrast that to equilibrium reactions, they never get to completion. They're never completed, right? They're always in that state of like, I don't know if flux is the right word to use, but it's dynamic. It's always like back and forth. It's never like completely stopped. So those reactions never go to completion. So just make sure that you're aware of that. And then let's see, I'm gonna sketch something to show you what it would look like from a plot standpoint, from a concentration versus time plot when we reach equilibrium. And I'm gonna use, let's see, are we good with this? Can I clear this from the screen? Or were you guys writing, or I'm not sure what's going on, how things are going on your end, but I was gonna draw a plot here. Okay, so I'm gonna clear this. Okay, and of course you guys can revisit the recording online if you want, so you can see this again if it is that you want to revisit and see the words again. So I'm gonna share a new whiteboard, and I'm gonna just show you a plot as to what equilibrium states would look like from a, wait, why is it showing that again? Oh, I have to clear the whiteboard. Okay, I have to clear this whiteboard because this whiteboard is what has the stuff on it. Okay, so clear all my drawings, and I'm gonna just sketch for you, right, a plot of concentration versus time, right? Because our concentration and how that's changing over time, essentially we can use that to show our equilibrium state, right? So our y-axis is concentration of whatever our product or reactant is. And of course, what's the units of concentration again, guys? Somebody just shout that out. I started you off.
Mole per dm cubed.
Mole per dm cube, that's exactly right. So mole per dm cube is your concentration. And what I'm showing you is an equilibrium reaction that involves hydrogen gas and iodine gas, and these are two diatomic gases. So for this particular case, we couldn't be using an open beaker, right, guys? Because I said when there are gases, you can't be having an open beaker and expecting that to operate as a closed system because your gases would escape. Well, see, already I'm writing. What did I do wrong here, guys, just now? This is an equilibrium reaction that I'm writing. What did I do wrong just now that I have to erase?
Means you have a forward arrow instead of the backward and forward one.
Exactly. Exactly. So let me correct that. So that's our irreversible, sign of irreversibility. So we have this. So that's gonna form what? Hydrogen, what is that? Hydrogen iodide gas. It's a gaseous reaction, gas phase. Can't use an open beaker. It's not gonna work, right? Because gases will escape and we don't want that because then that would throw off the equilibrium. Okay, so here we go now. So I'm showing the change in concentration of the reactant and product as equilibrium is approached, right? So think of it, let's walk through this now. Let's walk through this plot. On the left-hand side, we have hydrogen gas and we have iodine gas, and that's forming hydrogen iodide on the right, right? So over time, what's gonna happen to the concentration of the reactants? So our reactants are H2 and I2. What's gonna happen over time as this reaction proceeds? What's gonna happen to those concentrations?
Will they decrease, miss?
It will decrease, right? So let's say we're starting up here from a concentration standpoint. Over time, what you'll see is like it comes like this, and then it forms like this asymptote towards the with the x-axis, right? As we said, it never really goes to completion, so it never really ends. It never goes to zero. And so what we draw is like an asymptote, right? You know what an asymptote is from math? Where it's kind of like levels off with your axes. In this case, it's with the x-axis, right? So we show this, the asymptotic leveling off of the hydrogen gas and the iodine gas, right? These are our reactants. And what's gonna happen from this end, right? As equilibrium is reached, what's gonna happen with our hydrogen iodide gas? That's our product now. What's gonna happen there?
It will also decrease, miss.
It wouldn't decrease because what's happening is it's forming as a result of H2 and I2 reacting, right? So it wouldn't decrease. So what would happen is that what's happening in that concentration? It would be increasing, right? As the reaction progresses, right? Or as the approaches equilibrium. So how we draw that is we'll be like, okay, we have this coming up. This is our HI. And then as equilibrium is reached, it's leveled off. Same way that the bottom is leveled off, it asymptotically levels off. And so the concentration then of our hydrogen iodide rises, right? As the concentration of our reactants falls. And then now in this region here, let me get another color, let me use purple. In this region here, right? Equilibrium is reached. Right? Does that make sense?
Yes, miss.
So you see that nothing is zero, nothing is completely converted. So that's how you would show that kind of a scenario where you have the change in concentration of your reactants and products as equilibrium is approached. So we have that. How the equilibrium generally progresses, right? So we have that when the equilibrium is reached, there's no further change in the concentration of products or concentration of reactants. Reach equilibrium, it's a steady state. That's one other way of saying it's a steady state, right? So that's what equilibrium means, or how we can depict that. Okay, let's see. So then if it's the case in which, so what we just showed was equilibrium from the standpoint of a forward reaction, essentially, right? From a backward standpoint now, we could see, we can draw something like this. And so from a backward perspective, guys, what would happen for the reverse reaction? When the reverse reaction approaches an equilibrium state, like what would happen? How do you plot that? In a similar way that I just plotted it for, say, the forward.
Miss, with the HI be going downwards now, so it'll be decreasing, and then the H2 and I2 go upward because they'll be increasing.
Exactly. So let's see here. And of course, it's concentration dependent. So if we're starting with the same amount, and this is balanced, right? So we have 2 HI, so it's like 1 to 1 to 2. So if we're starting with the same amount of concentration of this and this, of H2 and I2, this is how it would look. You have 2 of them falling over time, then you have that one going up, and then now what I'm showing is when we're starting with hydrogen iodide alone, right? So just this hydrogen iodide alone. And so this is how it would progress. You would have your concentration of H2 and I2 rising. And of course, it levels off again, right? It's never gonna go all the way up and it's never gonna touch 0, right? Because it doesn't go to completion. So H2 and I2 would rise. So that's the level to which it rises, given the particular concentration here is, say, 0.04 mole per dm cube in this particular example, right? The number matters only from the standpoint of showing you like the steepness of the curve and how it changes in relation to when this is the amount of reactant that we're starting with. So like if this was like 0.02 mole per dm cube, these are concentrations I'm writing below it. Okay, guys? It's a 1 to 2 ratio, so of course it would be 0.04 that we're forming. So if we're starting then with the 0.04, then the amount of H2 and I2 would rise, right, like that, and then the HI would fall like that, and in this case the lines don't cross. It's like that. And the concentration of the HI then falls. And then, of course, in this region, is our equilibrium region, right? Okay, so that's just like a general plot as to how things work from an equilibrium standpoint. You're never leveling off to 0. You're never fully complete because equilibrium reactions don't go to completion. It's dynamic. It's dynamic. There's like a constant interplay between the product and the reactions, right? Rate of forward reaction equal rate of backward reaction. Concentration of equilibrium do not change. So that's why we have that leveling off. They're always the same because the rate of the forward reaction is the rate of the backward reaction. It's a closed system and it's dynamic, right? So those are all the characteristics that we just mentioned there. So are we good on that? Let's see. What's other tricky concept? We have equilibrium constants are very interesting to look at and to think about. That's your Kc, right? And you have to calculate your Kc. You have Kp, which is your equilibrium constant, which involves what? What does that Kp involve? Can anybody tell me? Where the equilibrium constant Kp come from? We have Kp and we have Kc. I can talk a little bit about Kc. And then, yeah, we can talk a little about Kc and then maybe we switch gears after that. So what do you guys think? Can somebody tell me what those are? What's Kc and what's Kp? So let me write it. Let me clear this. I'm gonna clear what I just drew, okay? I just cleared that. And let's talk about this idea of an equilibrium constant, right? So we have the most common ones that we think about are Kc and Kp. Does anybody want to share with me what those are? What are the
Yes.
differences? What do you know about this? Talk to me about this. And let me make sure that this is a capital K, right? Guys, it's not a small K, it's a big K. Because like we know that there's a difference between the big K and the small K. What's the difference? I'm asking you a bunch of questions at once. So let me back up. What is Kp? What is Kc? And why do I have to make sure that I tell you that this is the capital K versus the little k? Anybody want to go ahead?
Miss, Kc is equilibrium constant of concentration, and Kp is equilibrium constant of products.
Of products, or come again with that, with the P one. Kp,
Or pressure, Miss.
pressure, right? It's like
Yes.
from a pressure standpoint, from a partial pressure standpoint, right? And so because it's from a partial pressure standpoint, we know that it has to do with gaseous mixtures, right? Or gaseous equations, right? So that's when we would typically speak about a Kp, is when we're dealing with gases and gaseous equations, gaseous reactions, right? But Kc now is more universal, more or less, because most we can find the concentration, or we generally are given concentrations of a vast majority of reactants and products, and we can measure them, right? So the Kc now, you can calculate that from equilibrium concentrations, right? So let's see. Let me just write this out here. I'm gonna write it in a different color. So we can calculate this. We can calculate this from equilibrium concentration. So this is what this means, CONC, right? And then I guess, so from the partial pressure standpoint, it would be equilibrium partial pressures, right? So let me write that down, and then we'll just focus on C for now. Equilibrium concentrations. No, equilibrium partial pressures, right? Equilibrium partial pressures. Partial pressures. Okay. Partial pressures. So now we're going to focus on Kc now a little bit, because Kc is very interesting. So let's just kind of define how we would go about calculating that from equilibrium concentrations. So what we would say is that's our equilibrium constant based on concentrations. And so taking our equation that we wrote before, right? Let me write Kc big and bold down here so we know that that's what we're dealing with. We're dealing with Kc now, right? And so our equation that we wrote before was this. If you remember, when I drew that plot just now was, well, let me clear that, undo that. And I'll just write the equation without the parentheses, which means concentration. Let me not say concentration as yet. Let me just write out the reversible, right, equation, which is this, and HI. And it would be 2 for balancing. We have to balance it. Remember, we always have to balance our equations because otherwise it's not going to work, right? Especially when it comes on to moles and stuff like that and being balanced, you have to make sure that it's balanced, and you have to make sure that you have the correct state symbols, right? So now Kc, we said, is the equilibrium constant, and we can measure that. We can find that if we're able to measure the concentration of the products and the reactants at equilibrium. What we will find is that we can then use that to get our equilibrium constant. So you might remember that this is how you would write that from an equation standpoint. So you have your concentration that you're able to measure for all of your reactants and all of your products at equilibrium, and that would be your product. You write your product typically. Let me write it. Let me just tell you we're writing products, concentration of your products, right? Over the concentration of your reactants. And that would then be, right, the concentration of HI, right? And you might remember that where you put the stoichiometric, this number is up here. You remember that? Do you guys remember that? That's how you write it?
Yes, miss.
Okay, and then your H2 now is your reactant. So you write at the bottom, concentration of your H2, and then concentration of your I2, right? And this is a constant. And guys, why is it constant again? Because it's not, the concentration isn't changing, because the rate of the forward reaction is equal to the rate of the backward reaction. So the concentration isn't changing. So then overall, when you're in that equilibrium state, everything is constant. And then that's what leads us to this idea of a Kc, an equilibrium constant that's related to the concentration of your products and reactants at equilibrium. So are we clear on this? Is this clear, or is it something that you knew already? Where are we on this? Is this clear? Are we clear on this? So this whole thing that I just wrote for you guys is what we would say is an equilibrium expression. This is how we express equilibrium, guys. This is how we would write it. So then you know that, oh, this is equilibrium, they're in equilibrium, equilibrium expression, right? And so just a general rule now, the general equation, or the general way of writing this would be, I'm gonna write this in green in the corner. So generally you would have, say, your M is your stoichiometric coefficient that goes with A. And do you guys know what I mean by stoichiometric coefficient? I know sometimes when I say it like that, most people don't get it. But do you know what I mean when I say stoichiometric coefficient? So these small letters are the stoichiometric coefficients. This is the arrow, by the way. This is the reverse arrow, right? The equilibrium expression for Kc as a general, so we're generalizing now, right? And again, this is a big K. If we're generalizing it, it would be written like this. So the concentration of C raised to the stoichiometric coefficient, which is P. The concentration of D raised to the stoichiometric coefficient for it, which is Q, divided by your reactants now, which would be the concentration of A raised to M, and then the concentration of B raised to N. So this is a general expression for equilibrium expressions, right? So are we good on this? Are we all clear on this?
Yes, miss.
Okay, so I'm going to give you an example. And then what I want to do is I want to move on to how we can actually shift the equilibrium, because I think that that's where it gets tricky for some people. So let's see. This idea of Le Chatelier's principle and all that stuff. I don't know how deep I can go into this without providing some further background. But how do you guys feel about Le Chatelier's principle? Do you understand that stuff, or is that where it gets confusing? Do you guys understand Le Chatelier's principle? Like how you increase, if you increase the concentration, you shift it this way, or it moves, increases if the product increases relative to the reactants, the position shifts to the right, or the position shifts to the, like, do you guys remember that stuff? Are you comfortable with that? Let's see. Because that's where, I think that's where it gets cool, that's where it gets interesting. And that kind of plays into the other equilibrias as well. So like acid-base equilibria, it plays into it from that standpoint as well. So this, what I'm doing right now is just the fundamental, foundational chemical equilibria fundamentals, right? So Devanta said, all right, talk to me so I hear what you're saying. Where are the gaps in your understanding? So I think, okay, let me do this. Let me give you the example related to this expression, and then you tell me where your gaps are, and then we'll see if we can address it. Okay, how does that sound? I'm gonna give you a practice example of writing the KC here, and then we can talk a little bit more. So I just clear that. And I want you to write the equilibrium expression for ammonia formation as our first example. I want somebody to volunteer to write this on my screen so we can all see it. So I want somebody to write the KC for this. How you do go about writing that? Right? So write KC for this. Can somebody write it? Well, actually, let me balance it. This isn't properly balanced. There should be a 2 there. So how would you write the KC for this?
We'd put NH3.
NH3?
Square.
Mm-hmm.
Divided by N2.
Mm-hmm.
Then H2 cube.
Okay. Very good. All right. So you have the gist of this, right? You have this lock. You're comfortable with this stuff? Here's another one. Okay, everybody said I'm okay with that. So here's another one real quick, and then we move on. So another one would be 2SO2 plus O2 gas and so KC in this case would be, go ahead and tell me what KC would be here. KC would be
SO2.
SO3, right?
Yes, SO3 is square.
Mm-hmm. Mm-hmm.
And SO2 square. And oxygen gas.
Yeah. So essentially then what you would have to do if they ask you to find the KC, you would have to plug in the equilibrium concentration of these species in here, and then just plug that in your calculator, and that would tell you what then KC is, right? That's how you calculate KC. You're calculating your equilibrium constant, and you're using the equilibrium concentrations to get that. And then there's one final thing I want to show about equilibrium constants is the units. Units are very important in all that you do. any science subject, anything that you're doing, units is very important. It's exceptionally important for chemistry, for physics. Like you have to know what units, what's going on with the units, because I think oftentimes if you get lost in a problem, you can use the units as a way of guiding you to the correct answer, even if you don't really know what to do, but you know how the unit should work out, right? So for the case that we just wrote just now, it was SO3 squared, right? And then SO2 squared, and then just O2. That's what we just had, right? And then O2, right? So if we want to find the units now, what would be the unit of the top part from a concentration? Because remember, it's the units of concentration. So what would the units of the top part be? It would be mole dm cubed squared, right?
Yes, yes.
And then the bottom would also be, you'd have a mole dm cubed squared as well. That comes from the sulfur dioxide squared multiplied by the O2, which is also mole per dm cube, right? But what we see right away, guys, is that this and this would cancel, right? And so you end up with this in the bottom, right? Only this in the bottom is what you have. So the units of Kc in this particular case, for this particular reaction, would be 1 over mole dm cubed. And of course, by math rules, you know that if you bring that up to the top, to the numerator, it's essentially what you would get is what? dm cubed mole to the minus 1. Does everybody see that? So Kc has a unit in this case, but like there are cases in which Kc won't have any units. And can you guys tell me when that would be? When the constant doesn't have any units at all? What case can you imagine when that would be the case? When it would have no units. No units whatsoever. What case would that be? Okay, let's see.
Miss, could you repeat the question?
Under what circumstances would the Kc have no units? Like, well, when just now, it almost never have any units, right? It almost never had any units because the top canceled the bottom, but when the top canceled the bottom, there was one thing that remained. And because that one thing remained, that's where the unit came from, right? But if it was the case that the top and the bottom cancel completely, right? Then the Kc wouldn't have any units. So like let me just give a rough example. I'm not gonna give these things any name because I don't want to like confuse if it's not an actual. Oh no. Okay. So what I'm gonna do is I'm just gonna show you a case in which everything would cancel and you wouldn't have anything remaining. Right? If you have an equation like this, where you have A, let me say 2A. What would I say? Yeah, let's do that. We can do A plus B, right? Goes to C plus D. This is plus, guys, plus D. If you're supposed to write the Kc for this, you would write it like this. You would say Kc for that particular reaction, remember, it's always the concentration of your products, right? Divided by the concentration of your reactants, right? So in this particular case, what we see is that there are no superscripts, meaning there's nothing here up here, right? And there's nothing up here. It's essentially a 1, right? That it's raised to. And so the units of this would be mole per dm cubed. And it's the same for the other one, mole per dm cubed. And it's the same for the bottom as well. There are 2 separate concentrations down there. And there are 2 separate concentrations up top as well. And so when you divide these, right, what's essentially going to happen is that this is a multiplication. So essentially what's going to happen here, guys? It cancels out, right? This cancels this cancels this. And so your Kc in this particular example is unitless. And so we can categorically say that Kc has units of whatever. What we can say is that the units of concentration is mole per dm cubed. But we can't say Kc, the units of Kc is mole per dm cubed, because as we just showed, that is equation dependent, right? Does that make sense? I'm showing you guys the equation dependence of the units of Kc. It depends on the particular reaction and what those stoichiometric coefficients are, and if ultimately those cancel each other out. Okay, does that make sense?
Yes, miss.
Okay, let's see. Should we do a worked example, like a worked calculation, or do you guys want to go to Le Chatelier's principle? The Unit 2 students should be joining me at 5:30, but I haven't seen any of them as yet, so let's see. Yeah, I haven't seen any Unit 2 students as yet, so we can do, is either one of 2 things, guys. Is either we do an example calculation with equilibrium constant, and by that I mean like actual numbers, and you having to like figure out molar ratios to find numbers, and then we find the Kc, or we can maybe talk a little bit about Le Chatelier's principle, if you'd like, from a concentration standpoint, because we've only done concentration Kc so far. So what do you want to do? We want to see a worked example. Okay, so let's do that then. Okay, so let me clear that real quick. And so let's do this example. Let me see. Let us see. All right, so let's do an example here. And we're doing, and then while I'm writing this out, guys, tell me, write in the chat what resources you use to study. Do you have a textbook? Do you have YouTube? Like, what do you use to study? Drop that in the chat and let me know. I'm gonna write the example here now, okay? I'm just gonna write the example that we're gonna work through right now. And then, but in the meantime, talk to me and let me know what resources do you use to study. If it's a textbook that you use, write the name of the textbook. If you use study guide, whatever it is that you use, just let me know. I want to see what you guys use, if you use anything. Because I know a lot of people just don't really use textbooks. They just like look on YouTube and they Google everything or whatever the case may be. I want to know how you approach studying for your chemistry. How do you do your chemistry work? When you have labs, like what do you consult? So just write that in the chat for me while I write out this question, okay? CH3. All right, so this is our product. These are our reactants. All right, so this is, can anybody tell me what compound this is? From maybe from CXC, you probably know. It's propanone, right? It's a ketone, right? And this is hydrogen cyanide, and cyanide is very poisonous. We know that. And then our product, it's an addition product that is formed, right? This is the addition product. We're not concerned about its name. right? So let's see what you guys said in the chat. Fran says our teacher's notes. Nobody else responded. Devante says I use YouTube parts for study guide, sometimes the syllabus. That's very good. Very comprehensive. You're covering all your bases. And Devante, which school did you say that you attend again? Let's see. I know that Fran and Kimberly are coming to us from Trinidad. Oh, Devanta said Charlie Mont, Karina Mont Alverna. Okay, cool. And then I think that Beyonce and Anish are both from Fern Court, right? Correct me if I'm wrong. I think you're both from Fern Court. Karina said she uses study guide. Okay, that's good. That's good. Study guide is great, but what I want to suggest to you guys too is that you make sure that you have, so you're unit 1, so you'll be moving on to unit 2 next year, right? And I guess you're invested in chemistry for a reason. Perhaps you want to go to med school, or you want to be an chemical engineer like me. I'm a chemical engineer, that's what I studied in college. You want to make sure that you have a solid textbook that you can reference, right? Google is great, and you can Google a lot of things. YouTube is great, you can YouTube a lot of things, but like as you move through life and through your chemistry career, and as you go deeper in your knowledge of chemistry, it's good to have a reference book. Like I've had this book that I've had this since I was in 6th form, and that was a long time ago, guys, because I'm older than you. So like this book, I've had this book since I was in 6th form. Like when I bought this book, it was, you tell them how much it was, $3,500. And when I see this book in the bookstore nowadays, I think it's like, wait, how much does this book cost? I don't know, more than $6,000. But the point is, I've had that book like for this entire time, and I'm not telling on myself, but like when I was in 6th form, it was 2008. No, 2007, 2008, because I went to college in 2008, and I've had it since then. Like I took it with me through college, and I still have it, guys, in a good shape. So what I'm saying is you need to, I would suggest, I mean, I say you need to, I would suggest that you invest in a solid textbook. And like the fact that you're in unit 1, you still have time because you're going to need it for next year too. So I definitely suggest invest in a textbook. Okay. All right. So let's do this problem. So it's saying that at equilibrium, because remember, when we're talking about Kc, this is a Kc problem. When we're talking about Kc, we're talking about equilibrium concentrations, right? Equilibrium concentrations, right? That's what the Kc is that we're talking about. So first of all, let's do this. Who wants to write the Kc for this for us? Who wants to write the Kc here? Or tell me what the Kc would be from the expression, the equilibrium expression. Can somebody tell me that? And I'll just write it here real quick. What's Kc in this case?
It would be CH3 C. OH. Yes.
So it's this, and as you notice, there are no stoichiometric coefficients, right? So it would just be essentially an imaginary one, right? And what's in the bottom?
And HCN.
Okay, so that's our Kc, right? So the problem goes on to tell us the moles of stuff that we have, right? So I'm gonna write it out, but as I'm writing it, I'll talk. I spent the vast majority of these free classes that we've had. Today is the last day, was the last day for CXC as well. So I wrapped up the CXC classes and I spent the vast majority of our time going over the mole concept, right? And so this question is really gonna pull on your knowledge or your understanding of mole concept. So that's why I said all of that to say this, that this is essentially an application of mole concept to be able to solve this problem. So you're gonna see why I say that now. So they're telling us at equilibrium, so at equilibrium, right? They're giving us the moles of stuff that we have. We have 0.013 moles of this, of propanone, right? And we have 0.013 moles of this as well. So hydrogen cyanide, right? That's at equilibrium. They're telling us our equilibrium moles. And the addition product is this. Of this at equilibrium, we had 0.011 mole, right? Then, all right, so this is moles. So I'm just gonna point to that and show you that that's moles. And then they're giving us the concentration. Well, actually, no, not the concentration. They're giving us the volume, right? The volume is 500 cm cubed. And guys, let's use mole per dm cubed as our units. So what that means is that I need somebody to convert that volume to dm cubed for me. Because we're working mole per dm cubed. The volume that they gave us is in cm cubed. So what's this in dm cubed, guys? What's 500 cm cubed in dm cubed?
0.5.
Okay, so it's 0.5. So let's write that 0.5. 0.5 dm cubed. All right. So what's our first step then? We're trying to find Kc, which is this. It's in terms of concentrations. They gave us moles and they gave us volume. How do we find concentration when we've been given mole and volume? Concentration is what? What's the formula for concentration?
Mole divided by volume.
Exactly. So what's the concentration of these species here now? Can somebody tell me that real quick? So concentration is equal to moles divided by your volume. Moles divided by volume, and they give us our moles and everything is the volume. So somebody just run this math for me real quick. Tell me what all these concentrations are that we need to fill in here to calculate our Kc.
So the mole for the two reactants. Wait.
The mole or the concentration?
Yes, the concentration for the two reactants would be 0.026 mole per dm cube, and for the product it would be 0.022 mole per dm cube.
Okay, so then when you run the math on that, what do you get? What do you get for your Kc? So when you calculate it out, what's Kc? And when you're telling me what it is, tell me the units too, because units are very important. What are your units? And what is the magnitude? What's the number as well?
I got 0.022 mole per dm cube for the answer.
For the equilibrium constant for Kc?
Yes, miss, that's what I got.
Wait, how did you get that? Talk me through how you got that. For the equilibrium constant for Kc. Okay, so I see that Fran has the answer. Fran dropped the answer in the chat. And that's correct. But I want to hear Devonta explain to me how he got what he got so we can work through that. So Devonta, how did you get that number that you just said? And what were your units?
Yes, so what I did first was I just plugged in I plugged in the 0.022 divided by the 0.062 times 0.62.
Oh, it's a
So that
0.62, probably that's why it's 0.026, right? You told me that that's what it is. I don't know if that messed up your answer. So if you do 0. So essentially what you're doing is 0.026 squared. And that is what you're dividing 0.022 by to get your final answer. And I think Fran said it's 32.5. And the units are dm cubed mole to the -1, right? And that's because it's mole per dm cube on top, mole per dm cube on bottom cancel, 1 cancel 1, and then you bring up 1 to the top. So you get mole, inverse mole, and dm cubed, right? So this is your final answer for Kc. Does that make sense? So like Devonta, you have all of it right. You have the laying out right and everything and the calculation for the volume, for the concentration. But somehow when you plug in the numbers for Kc, something went wrong. So the number that you gave me was a little bit off, but the concept and the methodology holds, right? You have the correct approach and the correct methodology. But when you put in the numbers, somehow it messed up, right?
yes, miss.
And
Miss,
this
can the answer also be 3.25 times 10 to the -7?
10 to the -7. How would the -7 come in? Where do you get the -7 from? That seems off by some magnitude there. Like, is that for centimeter cubed or is that dm cubed? Because remember we had to do that conversion. So I
Yes,
don't know if
miss, I
that's,
did it.
is that what it is? Like, how do you get 3.25 times 10 to the -7? How did you get that number?
Miss, I times both the 0.026 times 0.026. And I got 6.76 times 10 to the -4.
And then what's your next step after that? So it's 0.02, 0.026, 0.026 times 0.026. That's 0.000676. 0.000676. So I got 32.54. That's what I got. 32.54 when I did that math. Yeah, Fran is saying make sure you use brackets, put the 0.026 in brackets. So yeah, but you have the right approach, you're on the right path. It's just the execution of the calculation that seems to be messing up a little bit. Let's see, so Karina is asking if this is it for today. Yeah, so we typically go to 5:30. Oh, it's already 5:45. Yeah. So typically how far we go, but like, let's see. Okay, I'm happy. It was very helpful, Karina. So this is your first class. You can unmute and talk to me, you can unmute and talk to me. We can stop here for today, but you can unmute and talk to me if you want. Because what I have, and I have this for the CXC students, I'm having some past paper marathons for them for April to prepare them for their exams. And the CXC is May 18th, and I think CAPE is May, I don't know why I'm missing it. I think it's May 5th. I think it's May 5th. I think I said this the first week when I it's the 5th, yeah, because I don't remember that. Okay, so what I said, and I'm gonna give you guys the same price that I'm giving them. And so let's see. Yeah, I know, Beyonce. I know. Maybe that's something I'll do on the Instagram. Maybe I'll do like a crash course on it on Instagram, or maybe I'll make a YouTube video on Hess's Law. Because like so far all my videos on YouTube are like live streams of this. So maybe I'll do a video on Hess's Law where like I kind of go through it, maybe I'll do that because we didn't get to do it today. So I'm happy to know that you guys enjoyed the session and learned a lot for today. But for the past paper marathon, it would be 1,500 per session. And so you guys are doing your exam on May the 5th. And so what that means is that I don't want to go too close to the exam. So like maybe we would have to start the past paper marathons on that weekend of the 10th. Yeah. So would you want it to be on a Sunday or a Saturday for you guys in this group? What would work best for you? So I would do 1 to 5, or I could shift the morning, but essentially it's 4 hours long. It's a 4-hour long session, right? So it's 1 to 4, it would be 1 to 4. But it's gonna clash with the CXC, and I don't want to like, yeah, because the CXC is 1 to 4.
Could we do it like Sunday from Saturday 1 a.m. to 4 a.m.?
Wait, what did you say? 1 a.m. to 4 a.m.?
Yes, Miss, like you said, it's 4 hours.
Wait, what did I just say? Wait, what did I say? What did I say? No, I'm confused. For the CXC, I'm doing Sundays. I'm starting the CXC on the 17th. I'll start you guys a week earlier. Or maybe even 2 weeks earlier. Let's see. 1, 2, 3, because I don't want to go too close to the exam. Like I don't want to be doing review sessions with you guys. I don't want to be doing a review session with you guys like the Sunday before the exam. Like I want you guys to space out your studying. I don't want you guys to like freak out, towards the end. And so I would rather not, I'd rather be done before May 1st. So you have that weekend to just decompress and to just sit with yourself and just put everything together for yourself in your head, right? So it would be, I could start next week Sunday with you guys. So that would be, so you'd have four weeks of past paper marathons. It would be April 3rd, April 10th, April 17th, and April 24th. So those Sundays, that's 4 Sundays, right? And so, yeah, so then if we start Sunday, April 3rd, which is this coming Sunday, with the 1 to 4, 1 to 5 is what I said, because it's 4 hours. Yeah, it will be 1 to 5. That's 4 hours, right? 1 to 5 on Sundays. And if it works for Saturday, because okay, so the CXC starting April 17th, you guys will start April 3rd. So there only would be 2 weeks of overlap between when I have to do CXC and you guys. And we'd have to figure out those dates, what those times would be. But I could do you guys from 1 to 4, 1 to 5 p.m. So let me write it down. Change the Saturday night. Okay, so Karina is saying that when the C6 starts, I can change it to Saturday night. What do you guys think about that? So we would start off next week, Sunday, April 3rd. So I'm gonna write it in the chat so you can see it there. So April 3rd to April 24th, because I said I don't want to come too close to the exam time. I don't like stressing people out like that. So April 3rd to April 24th, every Sunday. So Sundays, 1 to 5 p.m., right? That's 4 hours. And this is the price, this is the rate per Sunday, yeah. So it would be a total of this. And then as I told the other group, is that it's gonna be very involved, right? We've had a fairly small group so far, but of course I would be advertising it so maybe other people would join the group, but it's very one-on-one. But I mean, I say one-on-one. It's like a small group focus, right? Of just working through the problems. I'll be giving you guys supplemental information. So things that I think you should definitely zone in on and things that you need to know and just be able to like access rapidly. So I give you some supplemental information on whichever topics I think that you need that for, or maybe you can give me feedback on that. And then of course, that just like overall exam strategy and tips and stuff like that. So it's not like, oh, you're paying me your money to just like do the questions and that's it. It's more than that. And so I think it would be well worth it if you're interested. So approximately how many papers do you plan to cover per class? So how long is it that we say it's 4 hours, right? 1, 2, 3, 4, 5. Well, of course, Karina, this is dependent on how far we get. Like I have how many papers I plan to cover per class, as much as we can, as much as it's possible, right? But I also want to make sure, like, I want to leave room for questions, right? And for people to be like, Miss, I don't get it. Can you go over it again, right? And so how far we get is largely dependent on that. I mean, of course, yeah, so we'll start with the most recent ones, absolutely. And of course, I'm taking questions and having people tell me and ask me if things are clear. But of course, we're not gonna like get bogged down on one question for the entire 4 hours. We're gonna do as much as we can. So as much as we can. So to answer your question, as many questions as we can go through, we'll go through in that amount of time. That's my plan, and that's what I think that's reasonable for you. So Karina said, start with the most recent ones. Yes, let's do that. So my goal is to do as many questions as possible. And of course, how far we get is largely dependent on how many times I have to stop to like go into more details, which I don't mind. Like I don't mind sharing, okay, this is why. But what I would suggest is, I think for Unit 1, the free classes that I've done, span a wider range of topics. But I would definitely say ahead of that session, definitely go and watch back the videos that I've done on YouTube already, so that we're up to speed, so that I'm not spending any time in those past paper sessions explaining things that I've already explained in the class. Does that make sense? So like if it's something I've already taught on or touched on, make sure that you're up to speed on how I've already discussed it and described it and walked through it for these free classes, so that we don't spend time going over that when we could just be running through some past papers, okay? So that's where we are. So I'm gonna stop sharing my screen now and just see, I think some people have to run, so some people ran away already. So now it's just only the few of us remaining. So Beyonce and Anish, I said I'm gonna try to do a Hess's Law YouTube video for this week, because we weren't able to do it. So I'll just do that and upload it to the YouTube channel. So make sure that you're subscribed, and so you'll see that once it goes live. And I'll also like put something on Instagram, so you know that that video has been posted. So you can see that there. And then in terms of the past paper stuff, was it you and Anish who said that there are only 4 people in your class, something like that? Was that you guys? And Devonta is from Charlemont, he said. Devonta is Charlemont in, don't let me embarrass myself. Which parish is that in?
St. Catherine, miss.
Where is it?
St. Catherine.
Okay. I was going to say St. Mary. But yeah, so that's in St. Catherine. So definitely feel free to invite your classmates and tell them about the past paper marathons. And I think it's a fairly reasonable, if I do say so myself, I think it's a reasonable price for what you'll be getting. And I think a lot of students have said so far that they've benefited a lot from these free classes, that they've learned a lot. It's a similar approach to the past paper. It's a similar way in which I'm explaining things and walking through things. So I think that it would definitely be worth the money, which is not a lot in my estimation, but of course that's subjective, right? It's what you can afford. But I would love it if you guys could all attend, and definitely tell all your friends and tell your classmates. I know that once you start to get to that high level of chemistry, it kind of starts to thin out. There are not that many people there. And so if you've gotten that far, it's because you're committed to whatever it is that you're pursuing. And so it's definitely worth your while to get the best, preparation so that you can continue to excel. And so definitely share this information or this offering with your classmates who are next to you every day, grinding it out with you. So share this opportunity with them, and then come on, we're starting on Sunday, April 3rd, because you guys' exam is May the 5th. So we're starting April 3rd, and that will give us roughly a month to really go through in a thorough, methodical manner these past paper questions, okay? So what do you guys think? I will and you guys reach out to me too. If I don't reach out to you by the middle of the week in terms of payment and so on, and how to go about that, reach out to me and let me know. Devonta, are you following us on Instagram? I know Beyonce is on our Instagram. Anisha, are you on our Instagram? Follow us there so we can see the updates regarding past paper marathons, okay?
Yes, miss, I'll follow right now.
Okay, so yes, follow us there so you have access to updates and so on, regular updates, okay? Okay, guys, so it was great being with you guys today again. This is our last free class. It was great having you for this past, I was going to say 4 weeks, but we've been doing this for 2 months. We started in February. We did all weeks in February, and then we did 2 weeks in March. So I think that's 6 weeks. So I think that's pretty solid. Well, what I said is make sure you go back on the YouTube, watch the videos, and make sure you're up to scratch on everything. And then we'll start the past paper marathon on Sunday, April 3rd. Wait, go ahead.
What's the YouTube channel name?
It's LMD and STEM Academy. Let me drop a link in the chat right now, so you can just follow that and subscribe there. Okay, let me do that. Let me see if I just go on it now, like that. Okay, so this is the channel, and then you just subscribe, and then you share it with all your classmates. Okay, how many people are in your class, Devonta?
I would say roughly about 20 or so.
Solid. For Unit 1K, that's solid.
Yes, miss.
That's pretty solid. So definitely share the YouTube link with them and let them subscribe and watch. And of course, the past paper marathon stuff is a unique ID. So you have to pay your unique price, your unique fee. But if they're not able to attend that, or they can't afford that, then of course the YouTube channel will still be there. And as I said, I'll be putting other stuff that I maybe didn't get to touch on that you guys wanted to see. So Beyonce and Anish in particular requested Hessis Law. So I'll do a video on Hess's Law this week and upload that to the channel. So it's definitely still worthwhile to subscribe to the channel, even if you're not going to be doing the Passover marathons with us. So you can tell that to your classmates and just have them subscribe and watch what we're doing. Have them be on Instagram so they can interact with us and see what we're doing there as well, okay?
Yes, miss.
Did you see the link in the chat?
Yes, miss. I subscribed just now.
Okay, and am I pronouncing your name correctly? How do you pronounce your name? How do you pronounce your name? Is it Devante or Devante?
Devante, miss.
Devante. Okay. All right. Nice meeting you, Devante. And share with your classmates. Beyonce and Anish, look out for that Hess's Law video in this week. Definitely before the end of the week, it will be posted to the channel. And definitely share with all of your classmates as well, okay?
Yes, miss.
Okay. All right, guys. Have a great rest of your day. And I will see you on Sunday for the past paper marathon as you ramp up, as you close out this last month, this final month of preparations, right? So I'll see you next Sunday. Okay?